So my name is Li-Chia, and I was born and raised in Taiwan, and I moved to the US for some time, and then now I'm back in Taiwan. So I am with NYCU, and today I will talk about microscopy-guided to the reconstruction of nanodendrites in biosensors. All right, so here's my outline. First, I will introduce why biomedical sensors and also why nanodendrites for biosensors in particular. Okay, so why biomedical sensors? For me, it is connected to a personal story. When I was 3.5 years old, I was diagnosed with ITP. And for those of you who might know, it's basically your platelet level was very low. So for me, it was about 1 to 2% of the normal regular amount. And that means I basically almost died, but by mercy and grace, I'm still alive today. So looking back, that impacted me a lot, not just my personal philosophy, but also in my career, I do want to contribute to the field of biomedical sensors. And so you might ask, so what happened? Like, how did I know I had ITP? Basically, I was in kindergarten, and one of my classmates, he accidentally punched me or bumped into my face. So I got a very bad bruise. And because of it, my parents right away took me to the hospital, and then they realized I had ITP. So that was a very painful early detection, like not with sensors, but with my classmate. And now, and so now I do want to talk about sensors that can help us with early detection for many healthcare purposes. So why nanodendrites for biosensors? It also has to do with what we have been doing in the past few years. So just one slide talking about what we did for wearable sensors in the past few years. So many of you might know a lot of wearables on the market that focus on physical metrics such as your ECG, your heart rate signals. But what we were interested in was actually looking at biomolecular information, such as the ones coming out from your sweat, your saliva, and so on. So for this kind of purposes, we focus on electrochemical sensors. And as we were looking into electrochemical sensors, we realized the significant usage and benefits of having nanodendrites. And I'll talk about it here. So here's one example. For instance, this one we developed 2 years ago, nano nicotine sensor. So you can see on the bottom right figure, we have a CYP2B6, which is an enzyme for oxidizing nicotine. And then below it, we have the MUA self-assembled mono layer, as well as below it, we have the gold nanodendritic structure connected to our electrodes. So we realized by adding this kind of nanodendritic structures, we can significantly increase our surface area as well as increasing the sensitivity and stability of our sensor. And that was our reason for getting more interested in understanding nanodendrites. So experimentally, we saw the wonderful benefits of having dendrites. Now we want to ask if we can use a theoretical simulation approach to help us understand better. And that was the reason for this project. Okay, so talk about some basic ideas here. So our basic idea is first, we have two sources of two-dimensional data. First one coming from these top view SEM images. And then secondly, we have another one from 2D side view, which we can construct with Monte Carlo simulation side view. Now, the idea is if we can match our boundary conditions at the edges connecting the top view and the side view, then we can hopefully be able to reconstruct our three-dimensional structure. So that's our basic idea. Going deeper into our approach, so for this SEM top view, we first calculated this 2D density by looking at the patches within our frame. So we count all the patches, we divide by the entire frame to get our density for dendrites. And we make some assumptions here. So we assume our dendrites are homogeneous across our frame. So because of it, we can take the square root of our 2D density to get our linear density lambda on the top. Similarly, for our side view, 2D side view, when we do these Monte Carlo simulation, we can count our pixels and then divide it by the entire frame to find out our linear density lambda as well. And the idea is there will be one parameter, which I will introduce later, in this 2D side view. So by tuning our parameter, we can try to match our boundary condition properly. And by doing so, we can reconstruct our 3D model. So the idea is after this construction, well, you can see my mouse here, we will go back and compare our model with the SEM images earlier, and then as well as some more implication that I will talk about later. So that's our approach. So going deeper into our Monte Carlo simulation on the side view of our 2D system, we will talk about how we do it. So first of all, we start from a base layer of gold particles. And then with every iteration, we inject new particles into our frame. This particle will have a choice to either stick to our structure or to keep bouncing around with the probability P. So this probability P will be our parameter that we'll be tuning as we do this kind of Monte Carlo simulation. And of course, if you have multiple structures, say when your particle is bouncing into a place where it is surrounded by multiple structures, then we can assume 2 times P or 3 times P and so on when we have 2 or 3 more existing structures there. So that is our basic idea for this simulation. Okay, so once we have done so, let me go back a bit. So once we have done so, we are basically tuning our parameter P so that we can match this linear density here. And then once we have done this middle part, then we construct our 3D model using this selected probability P. So we did it by using Monte Carlo simulation again, but then in 3D. So here are some of the images we saw. So you can rotate this one, and then we look at it top down to compare with these SEM images we saw earlier. And then we calculated what are the dendritic densities using our model, and then we try to compare this one with the one from SEM images earlier on. So here are just different cross sections at different heights of our dendrites. So results and comparison. Let's across our entire board, basically our SEM image and our 3D model, they predict similar amount of dendritic densities. They are all within about 10%. And here are just 4 randomly chosen image comparison. So they are very similar in that sense. And that's very important because it shows that our model is able to give us a good prediction. And secondly, there are some more implications. So here's one. So with our 3-dimensional model, we have a parameter P that we introduced earlier. Now, once we validated this model, we can push our parameter to different extremes. So as we move around, we can try to figure out what's the upper limit of our dendritic density possible with our model. And as we did this, we were able to find that approximately, in general, we see an upper limit of around 75% of the dendritic densities. Now, once we have done so, we go back and survey all the SEM images in the literature. So we look for everyone's paper, we look at our own images as well. And we saw that their density most of them basically are within or lower than 75%. So that gives us multiple implications. First, it helps us to have more confidence regarding our model. And then secondly, it gives us a good reference number to have, because this kind of dendritic density is going to be very important in our biosensors. So those are 2 of these implications we have seen using this model. Okay, and then some of the future work and acknowledgement. Future work, we are interested in looking at not just our nanodendritic structures, but also what happens when we have different morphology. So say if you have nanoroll or nanosphere, different shapes of nanostructure, then what happens to our 3-dimensional model? Here is just one very preliminary idea. So we try to restrict the angles of our dendritic growth. By doing so, we can try to have the dendrites or the nanostructures growing in one direction versus just spreading across the entire frame. So bottom left is one example with preliminary preliminary nano raw, and then comparing with our right-hand side with just nanospheres. Okay, so finally, just some acknowledgements. I'm just here to speak for our group, but the entire work was done by everyone here. So I do want to acknowledge our Faith Lab members, grad students, postdocs, teammates, everyone. And they have been faithfully taking over ownership over the project, as well as inspiring each of us to do more exciting work. So with that, I thank you for listening, and I welcome any questions you may have.